Hi everyone, this video is going to be talking about the concept of half-life, which tells us a lot about how radioactive materials behave. And you can imagine these mysterious green blobs as hunks of some radioactive element, some radioactive nuclide. If you start with a hunk this big and then you come back a set amount of time later, specific to that element, what you're going to find is that in some amount of time, you're going to get to a point where half of that sample has transformed into something different via natural transmutation. And you're going to find if you wait that same amount of time and you come back, another half of that sample is going to be gone. So we've cut our remaining mass in half again. And if you come back again the same set amount of time later, you're going to find that that sample has decreased in size by another half. This unique property of radioactive materials is called half-life. And the big idea here is that it does always take a predictable amount of time for a radioisotope to lose one half of its mass. And that predictable amount of time just so happens to be listed on table N for your selected radioisotopes that we've got reference to. So as you're watching this video, have table N out and also have a calculator handy to help you with some of these calculation problems. So we can take this idea of half-life and use it to solve problems in nuclear chemistry. We know these radioisotopes are going to change over time, but now we can put a number to how long it's going to take for a particular nuclide to change by a certain amount. So this question is asking us, how long will it take a 10-gram sample of uranium-233 to decay to 2.5 grams? So I know I'm starting with 10 grams of uranium, and I want to know how long it'll take to get its mass down to 2.5 grams. I'm going to set this up using a table method that I like to sort of organize my thoughts. There are tons and tons of different ways that you can solve half-life problems. So if you find a mechanism that works well for you, stick to it. This is the one that I'm going to use just to sort of talk through what's going on in my head as I look at these problems. So I know I'm going to be tracking time versus mass, right? I'm trying to get my 10-gram sample down to 2.5 grams. I'm going to put that mass stuff over here in my right-hand column of my table. And I'm going to track time over here on the left-hand column. And if I look at my table N, I see that uranium-233 decays over a very, very long period of time. And that period of time is measured in years. So I'm going to keep track of years in this left-hand column. And right in the middle, sort of serving as my bridge between the two, is going to be half-lives, because I know for every half-life that passes, I'm going to lose half of my mass and gain a certain number of years. So I know that originally no years have passed, no half-lives have progressed. My original sample is 10 grams. We can change that. If we allow for one half-life to go by, we're going to divide this mass by 2, because that's what half-life means. Divide what you've got in half. So that's going to take us down to 5 grams. But we're not done yet, because we need to get down to 2.5 grams. And sure enough, we need to let one more half-life pass in order to get down to 2.5 grams. So after 2 half-lives, our mass has changed from 10 to 2.5, just like the problem wanted it to. Now all we need to do is figure out how many years have passed if it's been 2 half-lives. Well, on table N, it tells me that the half-life of uranium-233 is 1.592 times 10 to the 5th years. So every time one half-life goes by, we need to add on this value. And if you have your calculators handy, you know that 1.592 plus another 1.592 is going to give you 3.184 times 10 to the 5th. And that's our answer. Just add on your unit of years, and that's how long of a time period this is going to take. And you'll notice that this number, folks, if you're more comfortable doing it this way, once you've got your number of half-lives, you can just multiply that by the half-life that's listed on table N, and it's going to get you to the same answer. All right, let's try another problem. Here we've got an unknown radioisotope X, and it takes radioisotope X 30 minutes to decay to 1/8 of its original mass. I want to know what the half-life of radioisotope X is. So I'm going to, again, set up the same table. Lots of methods to solve these types of problems, but this is the one that works for me. I'm going to keep track of time over here, so it looks like I'm dealing with stuff in minutes. Half-lives is going to be my divider. And over on the right-hand side, I usually deal with mass. And here it's giving me mass in fractions. So I'll just keep track of the fraction that remains on the right-hand side of my table. So I know after 0 minutes, 0 half-lives have passed by, and I certainly still have my whole sample. I know I'm going to be decaying this whole sample as half-lives go by. So if we add on 1 half-life, I know I cut my amount of mass in half. So dividing by 2 gives me 1/2. 2 half-lives go by, I'm going to divide by 2 again and get 1/4. I'm not quite there. I need to get all the way down to 1/8. So after 3 half-lives, I'm going to divide by 2 once more, and that will get me to my 1/8 fraction that I'm looking for. So what this now tells me is that to get from our whole sample down to 1/8 of its original mass, it took 3 half-lives. And the problem gives us one more important piece of information, that 3 half-lives was equivalent to 30 minutes, because this decay process took a total of 30 minutes. So I know each half-life I had to be adding on a specific amount of time. I'm just going to represent it as like a plus x or something like that. So I know 3 half-lives went by, 3 half-lives was equal to 30 minutes. So all I need to do is divide that 30 up into 3 half-lives to get the length of 1 half-life. And that's going to be equal to 10 years. So if you really want to go in and fill in the table, you're going to notice that every single half-life is represented by, sorry, not 10 years, 10 minutes. We're dealing in minutes. My brain was still on the last problem, right? We're going to deal with 10 minutes for 1 half-life. So kind of working in reverse. Once we know the end, we can backtrack and figure out how much we must have had to have added each time we went down. Let's look at one more problem. In this third problem, I've got a sample of iodine 131, and it's decaying to 5 grams in a total of 32.08 days. I want to know what the mass of the original sample was. So I know where I end, but I want to know where I started. I'm going to set up the exact same table. Again, with time on the left and mass on the right. This time I am given mass in grams, so I'm going to put that right there. And here, again, my half-life is measured in days, so that'll be my time. And I'm going to have number of half-lives separate the two. Iodine 131 is one of the isotopes that's listed on table N, so you can find out information about the length of each half-life, because this time we're not going to know our original values for grams. We're going to know that after 0 days, 0 half-lives have passed, but we don't know how many grams we started with. So we're going to have to work over on this side of the table for a change. Once we add on 1 half-life, I know from table N that iodine's half-life is 8.021 days. I'll just use 8.02 to try and keep the numbers a little bit smaller at least. So after 1 half-life, 8.02 days have passed. After 2 half-lives, we're going to add on another 8.02 days, and that's going to take us to 16.04. That's not the 32.08 we need, so I'm going to add on another half-life, which means another 8.02. So 24.06 days have now passed. That's still not enough, so we need one more half-life to get us up to a total, again, adding on another 8.02 days to 32.08. We've now decayed for the amount of time that it wants us to. It's just a matter of backtracking with this grams thing to figure out where we started. So after these 4 half-lives, or 32 days, have passed, we know that we've got 5 grams. Well, we know every time that a half-life goes by, we cut our mass in half. So this is the result of dividing by 2 a bunch of times. So if we want to work backwards, let's just multiply by 2 to figure out where we started. So if we go backwards in time, we're going to go up to 10, then multiply by 2 again and get up to 20, then multiply by 2 again and get up to 40, and one last time to take us to our original value, multiplying by 2 will get us to 80. So we were going to have an original mass of 80 grams. So again, half-life, you're going to be tracking time versus mass, or a fraction, and remembering that a set amount of time for each radioisotope results in a decrease by 1/2 of your remaining mass.